So hello everyone. Today I'll be explaining data flow analysis and its applications in optimization decisions, a core concept in compiler design. The goal here is simple: understand how compilers analyze programs and we make smart decisions to improve performance without changing the output. So let's start with the basic idea. Data flow analysis, or DFA, is a technique used by compilers to track how data moves through a program. In simple terms, it answers the questions like where was the variable defined, and is this value still valid here, or can we reuse the previous computation? And why does this matter means because once the compiler understands this flow, it can speed up the execution, reduce code size, and use memory efficiently. So DFA is not just analysis, it directly drives optimization. To understand DFA, we need three key concepts. First, basic blocks. These are straight line pieces of code with no jumps in between. Think of them as the smallest units of execution. And second, control flow graph, or CFG. This is a graph where nodes are basic blocks and edges show possible execution paths. So CFG basically maps how the program can flow. And third, in and out sets. In tells what information is available before a block starts, and out tells what's available after it finishes. DFA works by propagating this information across the graph. And now comes the core logic, the equation behind everything. Out of a block is equal to what is generated inside the block plus what comes in minus what gets overwritten. In simple terms, gen equal to new information created and kill equal to old information that becomes invalid. So we are constantly updating the information is valid at each point. So there are two ways this information flows: forward analysis and backward analysis. Forward analysis means start to end, and backward analysis means end to start. This depends on the type of problem that we are solving on. Uh, and there is available expression analysis. This analysis check whether computation has already been done before. For example, if we compute b plus c once and nothing changes, we don't need to compute it again. So instead of recomputing, we reuse. This is called common sub-expression elimination. The steps involved in this process are identifying the expressions, track where they are available, and replace redundant computations. This directly reduces execution time, and this is one of the simplest yet powerful optimization. And this is the reachable definitions. Here we track where variables were last assigned. A definition reaches a point if there is a path where it wasn't overwritten. Why is this useful means? Because it helps us replace variables with known values and remove unused assignments. For example, if a value is assigned but never used, that's a dead code and we can remove it. So and this is a very important analysis. A variable is live if its value will be used later. If it's not going to be used, it's dead. And we don't need to keep that in the memory. And this is crucial for register allocations. The process involves computing which variables are live and checking where variables overlap and assign registers efficiently. So this directly affects performance at hardware level and makes a hardware level impact. And busy expression analysis, this is a backward analysis. An expression is called busy if it will be definitely be used before its variables change, and meaning we should compute it early and avoid recomputing later. This helps in lazy code motion and partial redundancy elimination. Basically, we avoid unnecessary recomputation in future parts. And these are some optimization examples. The first one is constant propagation, where replacing variables with known values at compile time. And second is dead code elimination, which removes the useless code. And third is loop optimization, which moves calculations outside the loops if they don't change. So all of these rely on data flow analysis to ensure correctness, because optimization without analysis is risky and DFA makes it safe. In real-world compilers like LLVM and GCC, DFA is heavily used. For example, LLVM uses SSA for efficient tracking, and GCC uses intermediate representations for optimization. But there are challenges. Loops require repeated computation until stable pointers make tracking difficult, and cross-function analysis is complex. So DFA is powerful but not trivial. And finally, coming to the conclusion, data flow analysis is the backbone of modern compiler optimization. It allows compilers to improve performance, reduce memory usage, and maintain correctness. And without DFA, most advanced optimization simply wouldn't be possible. Thank you.